Have you ever wondered why chemistry is the way it is? You know, why valence electrons are valence, why covalent bonds are covalent, and why hydrogen bonds just fine but helium struggles? Well, I'll explain all of that and so much more in today's video, where we'll go from basic mathematics through quantum mechanics up to chemistry. But first, okay, so imaginary numbers, which I've done like 1,000,000 times at this point from 1,000,000 different angles, but what you need to know in this video is that they are just the negative numbers for negative numbers. What does that mean? Well, it means that just like if you take a -1 and multiply it by itself, you get a 1. If you take an imaginary number and square it, you get a negative number. And that's really kind of it. I mean, sure, they do have some funky emergent properties because of that, but I've already made a dedicated video for the less simple numbers, so for now, let's move on to the functions. Now, functions are the easiest and best for our purposes described with graphs. So basically, imagine a number line. Heck, imagine 2 number lines. Now we can place a point on these 2 number lines, and this point, the further to the right it goes, the higher it goes on the first number line. The higher up, the higher on the second. I'll just move this point a bunch so you can get the idea. Now when it comes to functions, what you need to imagine is just a whole bunch of these points, where each one of them has their own corresponding first number and second number. When it comes to the functions, you can think of them as just tying the two together. So for example, function like fx is equal to x just means every single place where the dots have their y coordinate equal to the x coordinate. A function like f of x is equal to x squared means all the points where our y coordinate is equal to the x coordinate squared, and so on and so forth. And okay, it would be probably easier to see with more points, but the crucial thing to remember is that our representation with position here is completely arbitrary. This is something that's worth mentioning, considering how almost always functions are visualized with this sort of 2D grid. This is convenient where we have a single input, single output, but let's try instead 2 inputs, single output, where this will be still our x coordinate, this will be the y, but the output will be represented by size. Now if we set our function to be f of x and y is equal to 1 divided by square root of x squared plus y squared, then we get this. Lovely. But 2 inputs is not a limit. In fact, there isn't really a limit, so let's instead set to something like 3 variables. Now we extend our function into 3 dimensions, and I think you can see where I'm going with this. That's because if our 3 inputs are actual physical coordinates, then we can think of our function as a shape. That is because each point in our space will have some kind of value, so if we set our function to something like this, then this is what it would look like. Now, once again, the crucial thing to remember is that this is still a function and it still carries all the principles of the previous 2 and the one-dimensional function. It's just that we can interpret it as a shape. Okay? This will be important later. Next, we have a tad of probability. And I do mean just a tad, that's because not much is needed. So imagine a make-it intern with a basketball and a comically large hoop. Now this make-it will throw the basketball into the hoop and miss. Cause they're an idiot. But after a couple of tries, they'll make it in. Now let's imagine that we set up another make-it that will just take notes and note down all the stats of where the balls are landing and such. Now let's say that we repeat the experiment a bunch more times and ask the make-it for the stats. This is what the stats look like. The lit up areas correspond to how many times basketballs ended up in that place. Now we can imagine this probability as a function, where the input is the x and y coordinate and the output is the probability of the ball ending up in that spot. So in this case, I'll represent the x and y input as a plane, and the probability of the ball ending up in any place with height. Simple as it could be. Or is it? That's because if you think about it, all of these points are infinitely small, so that probability of the ball landing in that precise point, not the point right next to it, not the point higher, only that specific point is 0? Near 0? What is the function actually measuring? Well, this is the probability density function, and the problem does appear to be that we're trying to measure points that aren't quite 0. So basically, we can figure out what is the probability of the basketball falling into this area. If we want to get a point, then it won't be exactly 0, only will be the value that it is approaching. So like a limit as it's approaching zero. Or in other words, calculus. But we won't focus on that because it's simply surprisingly unnecessary for this video. Instead, I'll just keep it shrimple by saying that if we imagine our function as popping into 3 dimensions, then the volume under this graph is the integral of the function, and in this case, that integral is the actual probability. So if you want to know what the probability of the ball ending up is in that spot, all you need to do is just take the function, take the integral, lovely. But one thing that is important to mention is that even though our integrals are interpreted as the area under the function, or volume under the function, in reality they are actually kind of neither, because if you have a 3-dimensional function like this, then the integral would be the hypervolume? Yeah, I don't have 4 dimensions to visualize that, and that's the reason why mathematics has to stay an abstract and generalized concept, and why integrals are important in this case. But I digress. That's because next there is quantum mechanics, and you know what that means. Okay, we won't need all of that. So instead, let's just focus on the things we will need, like the underlying assumptions of quantum mechanics. So, first, what is a particle? Well, when I say the word particle, what probably comes to your mind is like a tiny ball, like a point in space, but the actual usage of the word particle is different. Most of the time when you hear the word particle in physics, it just means the lowest point of abstraction we're interested in. What does that mean? Well, in physics there are mainly 2 ways of modeling things. Those things are systems and particles. A system is when you've got a lot of pieces where the consequences of their behavior create some kind of physical phenomena. When it comes to particles, however, you just take some kind of properties as a given. So for example, when you have a proton, you can either treat it as a single standalone particle of a proton, or a system of 3 quarks. Most of the time, if you're studying physics, you approach protons as particles, mainly because if you have approached them as a system of quarks, then this video is so unbelievably redundant for you that I honestly don't know why you're even watching it at this point. The point is, what makes a proton a particle isn't some kind of magical barrier separating what's inside or outside of the proton. Instead, if you treat it as a single object, then that's good enough. You can call it a particle. So to sum up, particles aren't the dots or points or spots, they are just a way to model things, and if you don't believe me, just look up quasi-particles to find out all about the classic physics bangers such as phonon, plasmon, magnon, graviton, exciton, and honestly, I'm ready to give a tenner to the first person that will actually be able to explain to me why protons are a particle and not a quasi-particle. Now this is by no means an exhaustive or rigorous way to group physics models, but I still wanted to include it because it's actually great at explaining particles in quantum mechanics. So, what are particles in quantum mechanics? Well, they are points, or more importantly, we model them as points. So we model them as some infinitely small objects in space. Why? Well, kind of because it's the simplest way, and when this is what your average physics paper looks like, you'll take all the chances you can get when it comes to making things simple. So there, quantum mechanical particles are just points, right? Not quite. And here's where we enter the domain of the wave function. But in order to understand what a wave function is, we must first understand what it isn't. And so let's start where I always do, and that's with a box. This box has some kind of position, some kind of momentum, mass, energy, all that jazz. The 3 important things to mention are the fact that first, these values are measurable and absolute. If you have an uber precise measuring didgeridoo, then you can actually figure out perfectly what that position is, for example. Second, based on this position and velocity, we can figure out other things about it, once again, perfectly. So for example, if we push our cube, we know how much these values will change, and where our cube would end up after a certain amount of time. And then finally, these values can be anything you want, 5, 7, pi, whatever, you can change them however you like. Okay, so with that classical mechanics background, let's get into quantum mechanics. And in quantum mechanics, the first thing that jumps out at you is the fact that you cannot actually know the position of the particle, and that's not because you won't ever know where it is, only more because It seems like the universe doesn't know where it is. So basically the particle, instead of having any specific value for stuff like velocity and such, has instead a wave function which contains all the information. Remember our basketball function? Well, think about it this way. Before Make It throws a basketball in classical mechanics, if you know the force, if you know the starting position, you know all these things, then you can calculate where the ball will land, the exact spot with no errors. In quantum mechanics, however, it's literally impossible to figure out where the ball will land. And that's not because we can't calculate it, or because we don't have enough information, only because there is a certain amount of randomness involved. And as such, we cannot just give a point of where the ball will land. Instead, we need to give a function of probability. And so that function is the wave function. So basically, the wave function is the function that contains all the information about our particle. What does that mean exactly? Well, it means that our wave function takes in a point in space and gives us back a complex number. Here you can have a video that goes more in depth about complex numbers, but the basic gist of it is that it's just an imaginary number with a real number. So like 5 plus 3i would look like this, minus 2 plus 2i would look like this, a pi minus ei would look like this, and here I'm representing the real part with this axis, and the imaginary part of this axis. Simple as it could be. So we have our wave function, and then what we can do is we can just take it, multiply it by its own complex conjugate, and now we've got a function that returns a positive real number. For more information on why and how, check out my quantum mechanics series. But even though I won't tell you why or how, because that would take, frankly, way too long, I can tell you what, because this function we've ended up with is the probability of the particle. So it basically means that if we graph our function, then for our particle, it's really likely that we find it right here. Very unlikely that we find it right here, and right here you could, I suppose, expect it, but personally I wouldn't bet on it. Now this is a good spot to revise a bit. That's because if we combine all of our knowledge, then you should by now realize why we have to use this function, and we cannot actually in fact just check where the particle is. Normally, in classical mechanics, we just scan the space we have available, find the particle, and then just have a nice, neat number that we could use to determine the velocity or whatever. So like, in this case, we know that the particle is at x equals 2.66 or something. Then you can take that value, take a derivative in relation to time, and you get something like velocity, for example. In quantum mechanics, however, it is literally impossible to find that particle, because until we interact with it, the universe itself has absolutely no idea where it is. So instead what we do is we take the function, and we need to complete all the calculations with the probability in mind. But the oddness doesn't stop there. That's because there is also quantization, a topic which is comically easy to overlook, considering that it's where the quantum mechanics get its name from. But the basic idea is that our function is described by certain numbers, and those numbers can only be integers. So you can think about it as this function being the probability of position of the particle, and we can change the numbers describing the function, but we can only change them to be an integer, so either a 0 or a 1, but nothing in between. Yup, that's it when it goes to quantization. Now, believe it or not, this is actually all the background we require, which means that now we can leave the background place behind and move on to the applications. And what would those applications be? Well, imagine a two-dimensional particle with the function of probability which looks like this. So basically it's most likely to find the particle in the middle, shrimpo again. If we bring up a wall, however, then the probability shifts. I mean, yeah, if we bring an impassable barrier right here, then obviously we can't find the particle inside our wall. Instead, all of the probability shifts more to the left, because the particle cannot be found on the right. If, however, we keep moving our barrier, then it may be possible for some of our probability to leak. And once the probability leaks onto the other side, then what that means is that we can start with our particle on one side, but then as we keep measuring it, we may end up with it on the other side of the impassable barrier. And in this scenario, you might think to yourself, make it. This doesn't make any sense. How can our particle move through an impassable barrier? This would be teleportation. You must have gotten it wrong. But no. To everything you just thought, think better next time. You see, our particle isn't moving through our impassable wall, nor is it teleporting. It is merely just existing through it. I can explain. This is quantum tunneling, and basically the three things I want you to remember are: first, it is the direct consequence of the rules of quantum mechanics. Second, it would be absolutely impossible with classical mechanics. I mean, it would be just an object like going through a wall in classical mechanics, so yeah, impossible. And finally, it actually happens in real life. Recently, I've made a video with Flame about his research, and a really big part of the experiment was actually dependent on quantum tunneling being a thing, and it's shown that quantum tunneling is a thing. If you'd like, I would really recommend that video, it's great, but the point is, quantum tunneling does happen in real life. So I know that the rules of quantum mechanics may seem weird and unintuitive, but what I want you to remember is that if you follow these rules to their logical consequences, then you get even weirder behavior, and that behavior is what actually happens in real life. Okay, so that's quantum tunneling. If probability of something happening to a particle goes past the barrier, not the entire particle, only part of its probability, then it can quantum tunnel. This doesn't have to be position, it can be energy. Actually, in a way, energy would be position, no matter. The point is, you should now at least vaguely understand it. And finally, to round up the chapter, we have the particle in 3 dimensions. Now once again, in our reality, particles wouldn't really be 2-dimensional. Instead, they would be 3-dimensional. So despite the fact that right here I'm representing the probability with height, from now on I'll represent it with brightness. And that's because our particles would look more like this, where higher the brightness, the higher the likelihood of the particle being there. So in this case, if we have our particle, where is it? Well, it's somewhere in this cloud. Where in this cloud? I don't know. The universe doesn't know. All we know is that it's more likely to be found here than here. And so that's why particles can be both a point and a shape at the same time. From a mathematical point of view, this doesn't really make sense, but with the context it does, because when we're referring to particle as a point, we mean the particle. If we're referring to particle as a shape, then we're talking about the probability of us finding it somewhere. And so with that context in mind, we can simplify our function back into a sphere. And finally, move on to chemistry. And so now, in order to fully transition from quantum mechanics to chemistry, we need to take our particle with an arbitrary function and change it into an electron in the 1s orbital. And that's it. Yeah, electrons and electron orbitals are precisely what we've talked about so far. Electrons are the particles, and orbitals are just the possible wave functions, and that's why electrons can have different shapes. And more about that after the sponsor of today's video. Have you ever looked at your nickels before and thought, huh, that's awfully thin? Well, Nickels got you covered. With their groundbreaking nickel manufacturing technology, they can thick up these coins real quick. And who am I kidding? I'm not actually sponsored by Nickels. I can't even afford a nickel. But who I am sponsored by are my Patreons. And so I just wanted to take a second to thank you all for allowing me to continue making my videos. But anyway, the masks, the weapons, the chemicals, the videos, all of that I can only make because of my patrons. So thank you all so much. Anyway, okay, I feel like I should really hammer this point home. Remember when in chemistry class you've learned about the shells and the periodic table? Now, you might remember shells as 1s, 3p, 2s, 4d, whatever. But what if I were to tell you that all of these shells are just functions? 1, 3, 2, 4, that's a shell number, more specifically the principal quantum number. And don't be fooled by the sneaky letters right next to them. Those are also numbers, more specifically the azimuthal quantum numbers. And if we take the two together, then they are all the numbers we use in our wave functions of the electrons. So if you look up online what different shells, or more specifically orbitals, look like, then that is the wave function in 3 dimensions. This thing from before. And they are all specified by integer numbers because of quantization, as I've mentioned previously. So all the shells you've learned are just the possible functions that describe what our electron looks like. And the reason why they are discrete is because of quantum in quantum mechanics. So you can have the principal quantum number of a 1 or a 2, but nothing in between. That's quantization again. Next, the periodic table. What's so special about it? In order to understand that, we'll need to realize that wave functions aren't made equally. Basically, whilst you have your wave functions specified using these quantum numbers, some of them require more energy than others. You can think of it like a spring. A spring can be specified by a number of stretchiness, but higher values of this number require more energy. The same way, in our atoms, the general rule is that the lower the quantum number, the lower the energy required. And considering how everything in our universe loves having low energy, obviously our electrons would first like to start with the lowest possible quantum numbers. So a question might arise: why wouldn't oxygen have 8 electrons, all with 1s wave functions? Why does it have 2 on the 1s, then 2 on the 2s, then 4 on the 2p? I mean, you can clearly see that the right one requires more total energy than the left one, so what's up with that? Well, what's up with that is that Pauli exclusion principle exists, and it states that two particles cannot have the same quantum number. So that's why they cannot all stay in the 1s orbital. Hold on, make it. If they can't all stay in the 1s orbital, then one can two of them stay there? And that's a good question. And the answer is there are more quantum numbers. The first one is the principal quantum number. You can think of as separating orbitals by size. Generally, the larger the number, the larger the size of the wave function. Then the azimuthal quantum number separates them by kind of like waviness. So the more azimuthal, the more wavy, the more complex. Then the magnetic, which separates them by orientation, and generally the more waviness there is, the more possibilities for the waves to be oriented differently. Long story, would take a bit to explain. And finally, spin quantum number, which, well, it's not really spin, but it can be either up or down. And so just like orbitals are the possible shapes of probability that our electron can be in, and in each of the atoms we start with orbitals with lowest energy, and we move on to the higher ones. And on my favorite chemistry website, ptable.com, you can just go over to the electrons tab and see that as we go atom to atom, we increase the amount of electrons. And in this case, the higher the orbital, the higher the energy of the orbital, which is why we go bottom to top. Also, that's why we divide the periodic table the way they do. Due to reasons that will become apparent shortly, we only care about the valence electrons, which just effectively means electrons on the valence shell, so the outermost shell. And as such, we divide atoms in the periodic table by what is their valence shell. And that's the meaning behind the periodic table. And oh my, we just went from mathematics to quantum mechanics up to chemistry, and there is still so much left! Because what happens when two orbitals combine? So basically we have the s orbital with 1 electron, which looks like this, a p orbital with 1 electron, which looks like this, and actually let's add an additional 2 p orbitals just to make this simpler. Now we have 1 s orbital and 3 p orbitals. Chemists, please don't mind the viability of this, I'm trying to make a point here. Now let's say, as something that's definitely not a foreshadowing, that's outside of our atom, we'd have 4 points. These points would attract the electrons. Then what would happen is our orbitals would try to fit and stretch and reach these points, and it would turn all of them from a single s orbital and 3 p orbitals into a hybridized sp3 orbital. And so here's where we reach another important point. Orbitals can merge. The main rule describing this is that every time they merge, the amount of orbitals going in has to be equal to the amount of orbitals going out. So in our hybridization example, first of all, there'll be only 2 p orbitals and a single 1 s orbital with 2 electrons. But more importantly, there will be effectively 4 sp3 orbitals. That's each one of these legs, and the way they happen is we just take our underlying wave functions and we just combine them. So these are the wave functions for the underlying s and p orbitals, and these are new hybridized orbitals. You can think about it in one dimension kind of like this. We have our function which describes the probability of us finding the electron in the s orbital, and the probability of us finding the electron in the p orbital. Then if those two orbitals hybridize, then what we get is the new sp orbitals, and as such these are the new probabilities of us finding the electron. And so that's what hybridization is. But why would that matter? Well, it would matter because of bonding. So basically, we have two atoms, hydrogen atoms to be more exact, both of them with a single electron on the s orbital. As we bring them closer and closer, they merge together, and as such give us two new possibilities for their shape, the sigma and the anti-bonding sigma. What are those two new orbitals? Well, they are two ways you can understand them, the quantum mechanical way and the chemical way. First, we'll start the quantum mechanical way, which means treating our electrons as wave functions. And for that, we'll go back to particles in two dimensions, where this is what the 1s would look like, and we've got two of them. The first one belongs to the first hydrogen, and the second one belongs to the second one. Now, when we bond both of them together, this is just the equivalent of us adding both of these functions together. The important thing here is that our functions are complex, so they are both imaginary and real. And the crucial part is that we add them and then we do the thing to get the probability, not the other way around. And the reason why this is important is because if we add both of these functions like this, then this is what we get. Simple. As you can see, we get a larger probability in the middle, that is the bond. The electrons basically both pull the hydrogens to a point between them. But, just as a hypothetical, what if, instead of adding our wave functions, we subtract them? This would be equivalent to the wave functions having just opposite sign. And if we follow the equations, we can see that what we actually get is a wave function like this. That's because even though we get a positive number from squaring and such, we subtract them before we square. And you can see that this results in the wave function having a wedge in the middle, and the electrons more like pushing each other away. Now, which one of them is our sigma orbital? Well, both of them. This one is the bonding sigma orbital. This one is the anti-bonding sigma orbital. And so if we go back from quantum land to chemistry land, then you can see that whilst our bonding orbital is lower in energy than our s orbitals, the anti-bonding one is higher. Which is why when two hydrogens come together, both of the electrons drop onto the bonding orbital. The shape of the orbital brings them closer together, which is why they stick and don't drift apart. And the lower energy of the bonding orbital is what keeps them that way. That's because in order to break the bond, you need to add energy to the system. Hence why the bonds are stable. And so that's why you won't really find any hydrogen atoms on their own, and instead you will always find them as hydrogen gas. They are just that much more stable like this than like this. But what about if we add more electrons? Well, due to how each orbital can only house 2 electrons, if our atoms don't start with 1 electron each, only 2, then they first fill the bonding orbital with 2 electrons, and then that's it. Our other 2 electrons can't fit anymore. So where do they go? Well, they go to the only other option, that is the anti-bonding orbital, which this time requires more energy. And from there, it doesn't really matter if you think of it as energy lost being offset by energy that has to be gained, or the anti-bonding orbital repelling the atoms, offsetting the bonding orbital pulling them together, or as the wave function being less desirable because of the electrons appearing more in the atoms separately, because all of these models result in the same thing. Atoms not bonding. And so that is why hydrogen bonds and helium doesn't. What's more, this also explains why only valence electrons matter. That's because if you think about it, all of the electrons lower down are full enough so that one of their electrons will go to the bonding orbital and the other one will go to the anti-bonding, cancelling everything out. And so that's why only valence electrons matter. That's why noble gases are so inert. Their electrons offset themselves with the anti-bonding orbitals, and oh my, we finally reached the end. That's because right now you not only know what the rules of chemistry are, but also why they happen. And there is so much more I could mention, like the rotations of atoms, conjugated systems, resonance, metallic bonding, but it's already been 2 weeks since my last video, so unfortunately I don't have any more time.